Either astronomers who can understand the whole phenomenon, can predict it to within a second of time anywhere on the Earth, or a local native are equally in awe and reacting in the same way to this incredible phenomenon. It really left a big impression on me.
For 51 unforgettable seconds, Guillermo Gonzalez and thousands of others looked on in wonder at this rare astronomical event. Gonzalez would later reflect upon both the mysterious beauty he had witnessed in the North Indian skies and the factors that had made it possible.
Fabulous.
The requirements for producing a total eclipse of the sun are a luminous body, in our case the sun, an eclipsing body, in our case the moon, and then an observer platform, in our case the surface of the Earth. And they all have to be in a straight line in space. The apparent size of the moon in the sky has to be almost exactly the same as the apparent size of the sun in the sky. They're both about half a degree. The sun is 400 times bigger than the moon, but it's 400 times further away. So there's this coincidence people have noted for centuries, but they just say, oh, well, it's a coincidence, and shrug their shoulders.
As Gonzalez examined this rare alignment of sun, moon, and earth, he recognized the importance of these celestial bodies to the existence of complex life on our planet. The gravitational pull exerted by our moon, for example, is strong enough to regulate the Earth's climate by stabilizing its tilt and helping to circulate the warm and cold waters of its oceans, while our planet's distance from the sun permits both liquid water and an oxygen-rich atmosphere.
You have to have the right distance of the observer's home planet from its host star, and you have to have a large moon, and so there's this very strong overlap between the requirements for producing eclipses and the requirements for habitability, for having a planet that can support life.
In 1999, Gonzalez described this relationship between our survival and our ability to observe solar eclipses in the journal Astronomy and Geophysics. His ideas intrigued philosopher J. Richards.
I've been focusing my research in cosmology, and in particular on applying probability theory to the fine-tuning of the laws of physics. I had a strong sense that this evidence pointed towards some sort of wider purpose to the universe. Then I read Gonzalez's work, and I had the same feeling that he did, that perfect solar eclipses were sort of the tip of the iceberg, the first instance of an entire class of evidence that provides a way for judging if the universe is the result of a fluke or some impersonal process or the result of purpose or design.
In the summer of 1999, Gonzalez and Richards initiated a program of joint research. They began their study by considering a characteristic of solar eclipses little known outside the scientific community. These striking events are not only compelling to observe, they also open a portal onto the physics and chemistry of the entire universe.
Really, you can think of eclipses as a giant natural experiment set up that allows us to observe a part of the sun that's critical towards understanding how its light is produced in its atmosphere.
The fact that the Earth is going around the sun and the moon is around the Earth, and the sizes and the distances between the Earth and the moon and the sun are just so to give you a perfect solar eclipse is a wondrous thing, because it allows us to measure the constituents of the upper layers of the sun's atmosphere.
During a solar eclipse, the moon fits so perfectly over the sun that it shields its blinding light, providing astronomers with a view of the star's atmosphere otherwise impossible to experience. At the moment of totality, the pinkish arc of the chromosphere, the atmosphere's innermost layer, becomes visible, and with it a rainbow-like band called the flash spectrum appears when the sun is viewed through a prism. The eclipse of 1870 led to an understanding of the structure of the sun's chromosphere and the discovery of helium, the second most abundant element in the universe.
The spectrum is probably the single greatest source of information about a star. And it was during a couple of historic eclipses in the 19th century that astronomers figure out how the spectrum of the sun is produced. And they only were able to figure it out because of the particular circumstances during a total eclipse.
These circumstances are both precise and crucial. If our moon was slightly larger, it would partially block our view of the chromosphere and diminish its spectral light. A smaller moon would allow too much light from the sun, destroying our view of the solar atmosphere and the flash spectrum.
And so you have to have a nearly perfect match between the sun and the moon, so you don't hide the chromosphere. And that insight afforded by eclipses in the 19th century is what finally permitted astronomers to figure out how the spectra of distant stars are produced. Really, that opened up stellar astrophysics and allowed us to understand how other stars work, because distant stars, after all, are other suns.
The relationship between eclipses and scientific discovery was also revealed in the spring of 1919. On May the 29th, research teams headed by British astronomer Arthur Eddington photographed the Sun and adjacent stars in the Hyades star cluster during the darkness of totality. Later analysis of the pictures verified that the Sun's gravity bent light from distant stars traveling toward the Earth at the angle Albert Einstein had predicted. Einstein's theory of relativity, an idea that revolutionized our understanding of the universe, had been confirmed during a total solar eclipse.
And that experiment was only possible because the stars become visible during a total eclipse. They're very important in the history of science. And the best place in the entire solar system to view solar eclipses is from the surface of the Earth. I've actually calculated the circumstances for eclipses from all the other planets and all the other moons, about 65 of them, the major moons. And it's an amazing coincidence. The one place that has observers is the one place that has the best eclipses.
Within the gossamer light of a solar eclipse, Gonzalez and Richards recognized a fascinating connection between the factors necessary for complex life and scientific observation. But was this merely an isolated fluke of nature, or a glimpse at a principle and a purpose fundamental to the universe as a whole?
That was the million-dollar question that we continually had before us. What if those things that make a planet habitable also make that planet the best place for making scientific discoveries? That is, what if those rare locations in the universe that are compatible with observers like ourselves are also the best places overall for making observations?
For 3 years, Richards and Gonzalez meticulously tested their idea against evidence gathered from a wide range of scientific disciplines. In the 2004 book, The Privileged Planet, they published their hypothesis. The same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries.
In the book, we detail more than a dozen examples of this correlation between life and discovery. And these aren't quirky, marginal examples. Each treats a condition critical to its respective scientific field. Some deal with remote things, like the nature of galaxies. Others are much closer to home.
While a perfect solar eclipse was the catalyst for Gonzalez and Richards' hypothesis, their observations would never have been possible without another, more familiar example of the correlation between life and discovery: the atmosphere of the Earth.
It's striking when you see pictures of the Earth from the Apollo missions or other spacecraft, and you see this very thin layer of the atmosphere surrounding the Earth that sustains all the life that we know on Earth. And so you need a certain mix of elements to support a complex biosphere like ours. Not just any atmosphere will do.
Our appreciation of the Earth's atmosphere has increased significantly during the last 40 years as exploratory spacecraft have probed the solar system. These missions have confirmed that within the Sun's family of more than 70 planets and moons, the Earth is one of 7 bodies enveloped by a thick canopy of gas. Yet among these 7, only the Earth's atmosphere can sustain complex life. And only the Earth's atmosphere is transparent.